Section formula for ratio K, 1. Welcome, everyone. Let's begin our new lesson. Now, in our previous lesson, we explored the general section formula, where we looked at how a point, P with coordinates x and y, divides a line segment, OB, into a specific ratio, m1 to m2. However, as you move into more advanced coordinate geometry problems, you'll find that we often encounter scenarios where the ratio itself is unknown. In these cases, especially when you're trying to solve for an unknown, it is much more efficient and mathematically elegant to express that ratio as k to 1. In this session, we are going to walk through how we can simplify the standard section formula using this k to 1 approach, and I will demonstrate exactly how you can use this simplified version to find an unknown ratio when you're given the coordinates of a point. Understanding the ratio k, 1. When we talk about a point dividing a line in the ratio, m sub 1 to m sub 2, what we are essentially doing is comparing the lengths of the two segments created on that line. To make our calculations easier, we can perform a simple algebraic trick. If we divide both terms of our original ratio by m sub 2, look at what happens. The second term, m sub 2 divided by m sub 2, simply becomes 1. This leaves us with the fraction m sub 1 divided by m sub 2, followed by a colon and then 1. To simplify this even further, we can define a new variable, let's call it k, and set it equal to the fraction m sub 1 divided by m sub 2. By doing this, our ratio transforms from the more complex m sub 1 to m sub 2 into the much cleaner k to 1. It is important to understand the intuition here. This value, k, acts as a scaling factor. It tells us exactly how many times larger or smaller the first segment is compared to the second segment. As we will see in the next slide, using this single variable k instead of two separate variables will make deriving our new formula much more straightforward. Now that we've introduced the concept of moving from a general ratio to a more streamlined version, let's take a closer look at what this ratio, k to 1, actually means. Derivation of the simplified formula. Now that we understand the logic behind why we can express a ratio as k to 1, let's look at how we actually derive this simplified formula. You don't need to memorize a brand new formula. Instead, we are simply going to transform the general section formula you already know. First, let's recall the general section formula. As we saw in our previous lesson, when a point P with coordinates x and y divides a line segment OB in the ratio m1 to m2, the coordinates are given by x equals the quantity m1 times x2 plus m2 times x1, all over m1 plus m2, and y equals the quantity m1 times y2 plus m2 times y1, all over m1 plus m2. To derive our new version, we are going to perform a simple step-by-step substitution. We will take that general formula and replace m1 with the variable k, and replace m2 with the number 1. Let's see what happens when we plug those in. The formula for the x-coordinate becomes k times x2 plus 1 times x1 all over k plus 1. And for the y-coordinate it becomes k times y2 plus 1 times y1 all over k plus 1. Now, since multiplying any value by 1 doesn't change it, we can clean this up. The 1 disappears, leaving us with our final, simplified resulting formula. P with coordinates x and y equals the quantity k times x2 plus x1, all over k plus 1, for the x-coordinate, and k times y2 plus y1, all over k plus 1, for the y-coordinate. This version is much cleaner, and, as we will see in the next slide, much more powerful when you are trying to solve for an unknown ratio. When to use this formula? Now that we have seen how to derive this simplified formula, you might be wondering, when should I actually use this instead of the general formula we learned previously? Think of it this way. The general formula, where we use m1 over m2, is incredibly useful when the ratio is explicitly given to you, for example, 2 to 3. In those cases, you already have all your pieces, and you're just plugging them in to find the coordinates. However, the k to 1 form is specifically designed for a different type of challenge. It is your best friend when the ratio is unknown, but you have been provided with the coordinates of the dividing point, P. The real mathematical advantage here is efficiency. Instead of dealing with two separate unknown variables, m1 and m2, which would leave you with an equation that has too many unknowns to solve, the k-to-1 method allows you to solve for just a single variable. This reduces the complexity of your algebra and makes finding that missing ratio much more straightforward. Real-world application example. Now that we have derived the simplified formula, let's see how this actually works in a practical, real-world situation. Imagine a telecommunications engineer is working on a project to lay a straight fiber optic cable between two major hubs. Hub A is located at the coordinates 2, 3, and Hub B is at 8, 11. To ensure the signal stays strong, a signal booster is placed at a specific point, point P, which has the coordinates 5, 7. The engineer's task is to figure out the exact ratio in which this booster divides the cable between Hub A and Hub B. Let's walk through the solution step by step. In step 1, we first need to clearly identify all our known values from the problem. We have the coordinates for point A, which are x1, y1 equal to 2, 3. For point B, which is x2, y2, we have 8, 11. The dividing point P, which is x, y, is 5, 7. And following the method we learned in the previous slides, we will assume the ratio we are looking for is k-to-1. Moving to step 2, we need to set up our equation. Since our goal is simply to find the value of k, we don't actually need to work with both coordinates. We can choose either the x or the y to keep things simple. Let's use the x-coordinate. We'll take our x-coordinate from point P and set it equal to the x part of our simplified formula. X equals the quantity k times x2 plus x1, all over the quantity k plus 1. In step 3, we substitute our known values into that equation. So, 5 equals the quantity k times 8, plus 2, all divided by the quantity k plus 1. Now, in step 4, we perform the algebra to solve for k first. We'll clear the fraction by multiplying both sides of the equation by the quantity k plus 1. This gives us 5 times the quantity k plus 1 equals 8k plus 2. When we distribute the 5, we get 5k plus 5 equals 8k plus 2. Next, we rearrange the terms to isolate k. We'll subtract 2 from both sides and subtract 5k from both sides. This leaves us with 3 equals 3k. Dividing both sides by 3, we find that k equals 1. Finally, in step 5, we interpret what this number actually means. Since we found that k equals 1, our ratio of k to 1 becomes 1 to 1. In practical terms, this tells the engineer that the signal booster is placed exactly at the midpoint of the cable between Hub A and Hub B. As we move to the next slide, I'll point out some common pitfalls to watch out for when performing these types of calculations. Common mistakes to avoid. First, let's look at incorrect coordinate pairing. A very frequent mistake I see is students swapping x1 and x2. To avoid this, always remember the cross-multiplication logic. The k, which represents the first part of our ratio, must always multiply the coordinates of the second point, which are x2 and y2. Think of it as the ratio reaching across to the other side. Second, watch out for algebraic errors when solving for k when you are working with the equation where x equals the quantity k times x2 plus x1, all over k plus 1. You must be careful. A common mistake is forgetting to multiply the entire left side of the equation by the denominator, k plus 1, before you start moving terms around. If you don't distribute that multiplication to the whole side, your algebra will quickly go off track. Finally, don't ignore the ratio format. Sometimes, after all your hard work, you might end up with a fraction, such as k equals 2/3. Remember, our formula is based on the ratio k to 1. So, if k is 2/3, your ratio is actually 2/3 to 1. To present your final answer professionally, you should simplify this by multiplying both sides by 3, giving you a final ratio of 2 to 3. Now, before we wrap up our lesson, I want to pause and discuss some common pitfalls. Even if you understand the concept of the k to 1 ratio, it is very easy to make small errors that can lead to the wrong answer. Keep these tips in mind, and you'll be able to navigate these problems with much greater precision. Key takeaways. First, remember that the ratio k/1 is not a new concept, but rather a simplified version of the m1 to m2 ratio we studied previously, where k is simply equal to m1 divided by m2. Next, let's keep the simplified formula front and center in your mind. The coordinates of point P, which are x and y, can be found using the formula. X equals the quantity k times x2 plus x1, all divided by k plus 1, and y equals the quantity k times y2 plus y1, all divided by k plus 1. As we saw in our engineering example with the fiber optic cable, this specific form is your most efficient tool when you are faced with an unknown ratio and you already know the coordinates of the dividing point. It reduces the number of variables you have to manage, making your algebra much cleaner. Finally, keep an eye out for a special case. If you solve your equation and find that k equals 1, this tells you that the ratio is 1 to 1, which means the point is actually the midpoint of the line segment. All right, we have reached the end of our lesson, so let's wrap everything up with the key takeaways from today's session. I hope this breakdown of the k/1 section formula has been clear. Keep practicing these substitutions, and you'll find these problems much easier to navigate. Great job today.